My name is Gabriella Hug. I'm an assistant professor in Electrical and Computer Engineering Department and Engineering and Public Policy Department. Today's presentation is entitled, Can we make the grid work better without lots of new transmission lines? So in this figure you see a graphical representation of the electric power grid. We have the power stations in which the electric power is generated. We have the customers which consume the electricity. And we have in the middle the transmission system, which is the high voltage system, and the distribution system, which is the low voltage system. Now the transmission system is a mesh network. That means that power can flow multiple paths. So you could have two parallel paths and part of the power is flowing over one line and the rest on with the other line. Now, challenges which we're encountering is that, well, power flows according to Kirchhoff's law, so physical laws. That means it's given by the line parameters and where power is injected, where the power is flowing. So we can't influence that very well. So that means that when we have parallel lines, again, part will flow over one line and the rest will flow over the other line. Now, that wouldn't be so bad if we would have unlimited transfer capacity of each line, but each line is actually limited. So the maximum amount of power that we can transmit is limited. So let's look at the simplified version. Why is that now a problem that we can't transmit an unlimited amount of power? Let's assume we have these two power stations and we want to provide the electricity to the load on the bottom. Now, if we start generating with these two generators, at some point we will reach one of the lines which will actually reach the limit if the power flows according to the arrows that you see in the figures. Now, let's assume that the right generation plant is the one which is providing power at low cost, and the other one is more expensive. So that means that as soon as this line reaches its limit, we can't use the cheaper generator anymore to supply the load. Or another reason why we would want to be able to get rid of this congestion is that this generation plant might be a wind power plant. So if we can't use that anymore, then we basically have to spill available wind power, which is very valuable. So ways how we can solve that problem is build generation closer to load so that we don't need to transmit it that much anymore. Or we build additional transmission lines, which give us additional transfer capacity. Another option is to increase the capacity of already existing lines or transmission corridors by replacing transmission lines or also adding transmission lines. Another option, which I and my group are working on quite extensively, is controlling how power flows over the meshed network. Now, I was saying at the beginning that Kirchhoff's laws define where power is flowing. This is based on the line parameters. So if we're able to influence the line parameters, we basically can influence where power flows and basically cheat on Kirchhoff's laws. Options how we can do that are flexible AC transmission systems, high voltage DC lines, storage devices, and I'm going to talk about each of them just in a minute. What they are all able to do is that we can push some power from one line to the parallel system. That means that the power grid becomes more flexible, which exactly meets the needs of the future electric power system with a significant amount of variable renewable generation. Imagine that at some point in time you have a lot of wind generation on one side of the system, and that results in congestions on that side. You're able to push power to the rest of the system. However, if the congestion is on the other side of the system, you're able to, again, push some power to the other side of the system. Now, of course, how much you can push or how much you can influence the power flow is always limited. And one of the disadvantages of the different devices that I just mentioned are that they're still quite expensive. However, in my group, we're working on the algorithms on how do we control these elements if we have them in the system. So we're not concerned about how do we develop cost-effective solutions, but other people are working on that. Now, let's first talk about flexible AC transmission systems, or FACTS devices. These devices are based on power electronics. And what they're doing is influencing the line parameters, so the reactance of a line, which will decide how much power flow is flowing over that line. Now, So if we're placing that device in the line which is congested, what it allows us to do is push some power over the parallel system. That means that we can still use our cheap generator or use increased wind generation at that location and supply the load. So another device which you can use to influence power flows are HVDC lines. HVDC lines, what that means is you convert the power at one location into DC power and then at the end of the line convert it back into AC power. Or traditional power system is all based on AC power. That's why we're converting that into, we need to convert it into DC power if we're using that technology. Now the advantage of that system or that technology is that, let's say we're placing that in one of the lines, that we can convert the power, or we can decide how much power we want to convert on that end of the line and how much we transmit over that line. Again, that will allow us to reroute some power over the rest of the system. So power flow is becoming controllable. Another method how we can control power flow is by putting different storage devices at different locations in the system. That allows us to transmit power when there's enough transmission capacity and use stored energy when we need it. So again, in our little example, if we put the storage devices where you see it now in the graph, we could simply feed into the storage when we don't have enough transmission capacity and use what we have in the other storage device to supply the load. So that's also a way how we can influence power flows. So research questions that we're trying to address is how we should determine the control settings of these power flow control devices, independent of what device it is. So imagine if you have multiple of these devices in the system, one of them will influence how much power is flowing through the other one, and they might start fighting against each other if you're not coordinating them. So especially if there's a large amount of these devices in the system, it's very important to coordinate them. Another question is, what is the objective of the control? Do you want to minimize generation costs? Do you want to minimize reliability in the power grid? And so on. So generally, what we're doing is we're developing methods which allow us to do distributed but coordinated control. That means that we're assigning a responsibility of the control for a certain area in the system to a certain entity. And the idea is that these entities talk to each other, but in a very limited way, but that they're determining the control settings, which would also be optimal from the centralized perspective. So we want to achieve the overall optimal settings of all of these devices, which would also result in a good coordination of these devices. The general objective that we're looking at is improve reliability and reduce generation costs. So having a trade-off between reliability and generation cost. So that brings me to the end of my presentation. If you have questions, please feel free to send me an email.